Thank you. Okay, folks, any questions before I continue Galileo? Okay, Galileo continued his observations, and another major discovery that he had was discovery of satellites of Jupiter. Even with a good binocular, you can see these satellites moving around around Jupiter. At the first, he thought that he is just observing some background stars. But after a couple of nights, he discovered that these spots, these little stars, are really dancing around planet Jupiter. There were 4, and within a month, he was able to find out about their period of revolution around Jupiter. So it was a great discovery from astronomical viewpoint, but what was so important from philosophical viewpoint? According to Aristotle, the only center of revolution is the Earth. Everything in this universe must move around the Earth, the central Earth. Now, he discovered that around planet Jupiter, there are 4 objects are moving, and you observe them, you see that, find out about the period of their motion. Okay, again, what was the result? Aristotle was wrong. All astronomical ideas about Jupiter and I don't know, the center of motions were wrong. And now you see that the Earth was not the only center of revolution, and we found a new one. Then he turned the telescope to the Milky Way. In original Aristotle, Milky Way was what an atmospheric phenomenon. Aristotle had this idea that the concentration of some smokes or exhalations in upper atmosphere creates this Milky Way. Though Muslim astronomers corrected Aristotle, and they reasoned that an atmospheric feature cannot stay for centuries the same shape, the same way there, it should be something different. It should be, some said that it should be celestial, and some didn't have any explanation for that. So original Aristotle puts Milky Way as a kind of concentration of smoke in upper atmosphere, but when Galileo observed Milky Way, he discovered thousands of stars there. And it was again against Aristotle, against the cosmology that we had, against the religious ideas that we had, or religion didn't talk about Milky Way, but when you accept Aristotelian cosmology, then everything comes with that. And it shows that these religious authorities also didn't know anything about the nature of things. Then he discovered rings around Saturn, though he didn't see exact rings because his telescope was not that perfect. He considered them as handles or hands around Saturn. Okay, another discovery, very interesting. But what changed the story here and provided a clue to support heliocentric model was the observation of the phase of Venus. See, look from the previous slide up to here, up to Saturn's ring. Whatever he discovered was against Aristotle's philosophy or Aristotle's general assumptions in cosmology. So he discovered that moon was someplace like the Earth. Um, it was not pro-heliocentric model. It just showed that moon was not uh, made of, say, ether. It is like somewhere or on these deserts on the Earth. Or he discovered sunspots. Again, it was against Aristotle's philosophy that celestial region is perfect, no change happens there. The same thing in satellites of Jupiter, Milky Way. But when he observed face of Venus, it was a turning point. Why? Because there's no way, there's no way you create face of Venus the way that we observe with telescope by geocentric model. Only and only and only you can create these phases if Venus is moving around the sun. Okay, you see that what's happening here. On the one hand, you have uh, all new discoveries against Aristotle, supporting heliocentric model. But something more important happens here, and this is the way that we make our scientific statements, the way that we discover about nature. And that's why by experimentation, by using new tools, by using our mathematical knowledge. So when you see face of Venus here, you use your observation plus a simple geometry, and then make a major conclusion about the structure of the universe. At least show that Venus is moving around the sun, not around the Earth. So up to here, all discoveries were against Aristotle's basic concepts of cosmology, but face of the Venus was the first observational clue or verification of a heliocentric model. And it was that important which people started to actually blame Galileo that his telescope just distorting the reality. He put some, I don't know, spots on the lens. He opened the telescope, showed every piece to everybody there that there is no dots here, there is no points on spots on the lenses, and it is just as simple as the lens that you see. It is not distorting. And he had a very interesting statement. He says that, okay, this is the same magnifier that Pope uses to read the Bible. If it distorts everything, then it distorts the way that Pope reads Bible, because that time it was common to use magnifiers, the same lens that you use in a telescope as magnifier to read books. Okay, in one of the first observations that he had was in Venice, and there's a big tower. They rebuilt it. It was ruined later, and he took all these noble people and religious authorities to the top of that tower, and there not only he showed the power of this telescope, that they were able to see ships, the tip of the ships, the tip of the mast of the ships before they approached, and at the same time they practice astronomical observations. Now again, put yourself in that atmosphere. All knowledge that you have right before this observation is what? Aristotle's cosmology, geocentric model. Now you do one observation, and then you have to make a decision to do what? You have to change your entire mind. You have to change your entire philosophy. So that was not that easy. You had to observe more and more, to visualize what's happening. And some people, again, as we will see later, that they thought about the validity of experimentation. So you do one observation in 5 minutes and change whatever all these educated people, learned people had for 2,000 years. How come that one observation cross out thoughts of thousands of people in thousands of years? Oh, okay, it is not acceptable. How can we trust on the results of observations? How can we trust that all observations gonna yield the same results? So it is a long story. We're gonna talk about it in the third book that we read by Dolnick, The Clockwork Universe. Another thing that we see made story difficult for Galileo, and Galileo and Church started to have a clash. By this time, Galileo, all new ideas from Copernicus' heliocentric model to Kepler to Tycho Brahe to many other thinkers, they published their ideas in Latin. Latin was high-rank, elite language for scholars, and regular people, they didn't know anything about these things. They were using their own language, their common language that they had. Galileo published his discoveries in plain Italian and made it accessible to anybody who was able to read and write. And just think about that the height of Renaissance that time. And we had a lot of educated people, and publication was there. They immediately published these books. Specifically, one of the publications that Galileo had, which put Church and Galileo and these new discoveries in front of each other, was the letter he wrote to the mother of Medici, his supporter, the Grand Duchess Christina. And there, for the first time, we see a very beautiful description of relationship between natural science, new discoveries, and religion. This is a long letter. I posted it online, I believe, last week, but I'll double check it. It is among the recommended readings. There, to make long story shorter, I summarize it in this way, that he says that, okay, folks, everybody agrees that God created the universe. Yes, that is the greatest creation that he had. Then God created human being, yes, and gave us a CPU, reasoning and thinking, what's called machine here, which is doing very well, because if our CPU is not working very well, even we cannot know God, we cannot realize about universe, we cannot create mathematics. It shows that this part is working very well. It has a very good logic. It can distinguish that, I don't know, 5 is bigger than 3, or I'm just adding myself, the sum total of some of the angles of a triangle is 180 degrees. Okay, we have the setting right now. Now, God later sent us Bible, his own words, and from day one, we had to interpret Bible. Why? Because there are a lot of metaphors there, a lot of stories. You cannot take them literally. How can you take it literally? Because there are a lot of things you can find there. God sitting on a throne. He doesn't have a body like us. You cannot attribute these things, human things, to God. But there, God talks in Bible for common people with common people's languages and their understanding. And that's why we interpret Bible. Then he asked this very beautiful question. When we discover a truth about the real creation, the physical world, the way that God created, and we are sure that is true, and we prove the truth by using our reason with mathematics, with observation, then should we interpret Bible based on that truth, or we should interpret physical world based on Bible? Which one is valid? And he concludes that obviously you see God's real creation and you verify that, and you do observation after observation. You see that again, I'm adding here Venus has phases. Then you have to interpret Bible based on that, not the absolute the truth that you see based on Bible. So it was not acceptable by church, because who's this guy coming with a telescope and two observations? He wants to shatter all the I don't know, institute that we had and established there for a long time. Then they put more and more pressure on Galileo to stop talking about heliocentric model. They put Galileo in house arrest, and there Galileo started to do his own publications. He already wrote this book, but later he published it, the Dialogue on the Two Chief World Systems, which was published in 1632, and it is in Italian. And again, I ask you, please find this book. It's online, it is free. And you see that in 3 days, 3 people are discussing the structure of the universe. Salviati is the good guy, Copernican guy, Sagredo is the mediator, and Simplicio is Aristotelian guy believing in geocentric model. And if you don't know anything about classical astronomy, heliocentric astronomy, after 3 days, you find out that heliocentric model works better than geocentric model. And it was in, as I said, plain Italian language. He used a lot of examples, not in a very complicated language. Everybody read it, understand what's going on. So then you can think about the spread of the wars among all educated people, and they learned little by little about not only heliocentric idea, but Galileo's approach, how to prove them, how to use experimentation, how to use telescopic observations. And he also used some of his knowledge from Demoto, the older books that he had before telescopic observation, in his new book, Discourse on Two New Sciences, which was published in 1638. In this book, he really introduced 2 new sciences: kinematics and the strength of materials. There, he takes stuff from his early publication about the world and puts here to discuss motion, local motion, projectile motion, free fall, and also strength of material. And for the first time, he come up with some new thoughts and ideas about what's going on inside matter, in theory of matter. I'll talk about this in a minute. So this is the cover page of, sorry. This is the cover page of Galileo's Dialogue on the Two Chief World Systems. Everything is about astronomy. This is a page from Discourse on Two New Sciences. And all these drawings that you see are from Galileo. He was a very good painter. He was master of color painting and watercolor, I'm sorry. And what you see here, how did people that time know about what kind of stone they use to make a pillar or to make the base of their buildings or a bridge? How did people know that time about what kind of lumber, wood they used to make a ship hull? Everything was based on trial and error, or the knowledge that they gained through generations. Now we see that Galileo tries to make it scientific. What is the relationship between the length, cross-section of a beam and the amount of the force that you enter on it and the breaking point? So you practice it using what? Experimentation, doing measurement, and then come up with an empirical rule. You can immediately connect it to the same way that we make buildings right now. It didn't happen right after. It took a long time to enter this type of thinking into university education and ask engineers to think like scientists. But it was the starting point. That is why it is so important both in history of science and history of technology. So in Discourse on Two New Sciences, in these two new sciences, which were kinematics and strength of materials. I'll talk about the kinematics in a minute. In a strength of materials, he talks about, he asks questions like this: why a marble pillar is stronger than, I don't know, you make a pillar out of mud. What's going on inside these particles? What is the cohesion between them? What makes some material stronger than other material? What is the surface tension? What is the size effect? Why cannot make a ship with, I don't know, 2 million tons of weight? Okay. Questions like, again, condensation, rarefaction. How does light propagates and travels? He tried to even measure the speed of light. Obviously, that time they didn't have any time-keeping device to be that sensitive to do all these measurements. But in all these questions and in all these studies, he had an experimental approach and a mathematical approach to collect data, to do all measurements, and then finally try to find a mathematical relationship between things happening around. So in free fall, again, he tried to do experiment to see if heavier objects are falling faster than light objects. And after over and over experimentation, actually, he made an inclined plane, you will see in a minute, to slow down gravity, and rolling balls. He started to collect data that each second the ball travels how much on this inclined plane. And we have a short video, we're going to watch that. So all these things show what? A new approach in discovery. I have to add here something, though we're going to talk about later a lot about that when we reach to Newton. we drop this ball, okay, probably we already talked about briefly. You can drop this ball over and over. You may have two types of questions, why question and how question. Why question is explaining why does it fall. You can say because of gravity, because of curvature of space and time, because, I don't know, some spirits, they pull it down, and you answer in this way. But how question is a very detailed question. How does it fall? It falls from point A to point B. Okay, you measure that, it falls in time t, and then you find out that it has a velocity, distance over time. Then you be very careful to see how does it fall. Does it, is it falling with uniform velocity with no change, or its velocity changing? You find out its velocity is changing. Then you invent a new concept, change of velocity over time. You call it, I don't know, acceleration. And then you describe how does this simple free fall happens. After long term of experimentation and observations, Galileo was able to find a mathematical relationship in free fall. He discovered that distance that a free falling object travels is proportional to the square of time. And in modern physical books, you find it as d or s equals to half of gt square, which this g is the acceleration of gravity that we have on the Earth. And then Galileo concluded that if we have vacuum, if we have a cylinder with no air, and you drop things, a feather and a stone, they're gonna fall at the same time. And actually, it was in Apollo 12 or 13, I don't remember, not in Apollo 11. They practically practiced that. They had a hammer and a feather. They dropped them, and they fell on the surface of the moon at the same time. So here you see his observations on inclined plane, and after many observations, he was able to make a mathematical description of free fall. X equals to, or distance equals to, half of at squared plus vt. Don't go to a physics part, it is not a physics class, but here we see a major change. If you open Aristotle's book, you don't see experimentation, you don't see mathematics there, you don't see what's called mathematical expression of motion. It is just based on philosophical principles. Now we are changing towards what? Performing experiment, changing the condition of experiment to change the kind of data that we have, and then recording everything, creating numbers, and making our knowledge based on those observations and numbers. And that is what the way that practice science right now. This is the inclined plane that Galileo used. It's not the real one. I believe it is reconstruction of that inclined plane. And he also tried another path here, a round path. It is from Galileo's museum. Here, yeah, we have this experiment done by Jim Khalili, one of the best interpreters of science located in London, England. And I have to add here something, that time Galileo didn't have a timekeeping device to measure the time. of travel of this ball. So he tried his pulses. It was not a good timekeeping device. He used, he had an idea how to use a pendulum, but again, he didn't have what you call a working pendulum clock that time, and he used what we call it clepsydra or water clock. You can have a flow of water and measure time by the amount of water you can collect in that time interval in a cup. And based on that, you measure, so you have more water in this cup, it means that more time is elapsed. Now let's watch this. I hope it works. And then you learn how difficult was these experiments that time.
When you drop an object, it's actually quite hard to tell if it falls at a constant speed or picks up speed as it drops. Even in slow motion, it's pretty hard to tell. But Galileo realized this. First, drop an object a very short distance. It lands with very little impact. But of course, drop it from higher up. This time, the ball easily breaks the tile, which means it must have accelerated, gaining in speed and momentum as it dropped. Galileo had identified something fundamental to all falling objects. They accelerate. He realized there might be a way to measure how much falling objects gain in speed. What he devised was the first ever attempt to measure gravity itself. He built a long wooden ramp, rather like this, that he had sloping at a shallow angle. The idea was to roll balls down the ramp and measure their acceleration. The crucial thing is that the ramp had to be at this shallow angle to reduce the effects of wind resistance. It also meant that the balls would roll down slowly enough to give him time to measure their speed. But the big problem was this: how do you measure time accurately in an age when there were no accurate timepieces, let alone stopwatches? Well, Galileo came up with an ingenious idea involving the flow of water, essentially measuring time from the amount of water collected in a cup. So we're going to try and repeat Galileo's experiment. I say we because I have a couple of willing volunteers, Gavin and Joanna. 3, 2, 1, go. Stop. Okay, there's one. Now, if you come down a quarter of the way down the ramp, go. Stop. Okay. So now half of the way down, go. Stop. Okay, and then 3/4 of the way down, go. Stop. Right, turn the tap off. Okay, so we have our 4 measurements, and I can see a progression from fuller to emptier. But what we need to do now is find the mathematical pattern by weighing carefully the water in each glass. Weighing the water should give us an idea of how long each roll took. And in our experiment, these were the results. Now, there's one immediate thing you can tell. The ball really sped up the longer it rolled. In fact, our results seem to show that the time it took to cover the first quarter of the ramp was about the same time it took to cover the next 3 quarters. Right. So we have a strong hint of a mathematical pattern. Now we'll see if we're right by placing bells along the ramp, intervals which are based on the results. Okay. This arrangement looks a bit strange because the gap between the first two bells is much shorter than the gap between the third and fourth bells. But that's okay, because if we've got our calculations right, the ball starts off slowly, so it covers a shorter distance, and as it picks up pace, it'll cover longer and longer distances. So we should hear the bells ringing at equal intervals in time. Go. Beautiful. So what does this all mean? What's the mathematical formula? Well, this is something that Galileo worked out. Let's say from the start, the ball covers a distance of 1 meter in the first second. After 2 seconds, it'll have covered 4 meters. After 3 seconds, 9 meters. After 4 seconds, 16 meters, and so on. If you recognize this progression, you'll see that distance goes like the square of time. Galileo had found the rate at which gravity speeds up objects. And he'd found another fundamental principle. You can measure the strength of gravity by how much it causes falling objects to accelerate.
Okay, if you're interested in these type of things, this videos by Jim Khalili is really interesting. He had a lot of videos from quantum mechanics to gravity to relativity to many other things, and history of science, specifically history of electricity and so on and so forth. Anyhow, so back to Galileo. Galileo, in analysis of motion and projectile motion, made another major discovery. In Aristotle, when you move something, we call it violent motion. I'm not talking about natural motion up and down. Imagine you are rolling this ball. Okay. So I put this ball here, okay, and I roll it here. I hope it doesn't fall on my computer. So it rolls and it stops. In Aristotle, it stops because when it moves, it creates a vacuum behind, and then air rushes to fill the gap. And when it fills the gap, it stops. Galileo started to ask question in a different way. He said that when it rolls, it is under different forces. It is the force of gravity down, not exactly the same concept that we are using. It is heavy. There's the heaviness is a factor here, and then it has frictions with the surface. It has friction with air, and it says that if I remove all these things, what can happen? His conclusion is revolutionary again. He says that when there is no external force acting on it, it should move forever. If you remove air and it doesn't have any friction with air, it's going to go forever. This is a new idea. We call it inertia. It is the first law. It is very, very similar to first law of Newton. And in this sense, when you change the state of motion of an object, the object remains in new state of motion forever unless an external force acts on it. In Aristotle, you need a finger behind object to move it all the time, or a mover to move it. And if you remove them, it's going to stop. In this new concept, Galileo says that if you change the state of the motion of an object, it remains in new state of motion unless an external force acts on it. This is the basic concept that we are using, obviously, when we adopted Newtonian inertia. You send a space probe towards Mars. All the time, its rockets are not working. You reach to a speed in a space and then shut down the rockets, then it continues in that direction forever to the end of universe, unless an external force acts on it. This is the concept that we are using when we buckle up, when we have seatbelt. So you drive, you stop, you can stop the car with brakes, but you're not bolted to the seat. If you don't use your seatbelt, you continue moving because you have this inertia. So he combined this idea with projectile motion, and those days were the heydays of making cannons, the wars that we had in Europe, but it took a while again for military engineers to use Galileo's ideas in their projectile technology, but he distinguished that when we have a projectile motion, actually you can break it into two components, two what we call it vectors. One component never changes. It is inertia. You change the state of the motion, and imagine it happens in vacuum, but we have gravity. So one component is not changing and remains the same, but the other component, you can actually break this diagonal into two vectors here, horizontal vector and vertical vector. And you see that horizontal remains the same, but vertical changes. And from a maximum reach to zero, and from zero, it reached to maximum. So it was a major change in understanding of motion, understanding of projectile motion. He invented this new idea that when there is no external forces, objects keep the state of the motion that they have. And it was the beginning of another major revolution came with Newton, which we're going to talk about them next week. So another aspect of Galileo was applying scientific knowledge in engineering. According to one of the historians, he said that Industrial Revolution didn't start with Galileo, but Galileo had a direct impact on Industrial Revolution because he tried to understand the machines based on input and output and think about this, how to increase the efficiency of machines by using the mathematical knowledge that we have coming from physics, coming from different branches of physics. So he analyzed machines that they had, pulley systems, gear systems, even clocks, because again, in time of Galileo, we have a great achievement in making of mechanical clocks and mechanical planetariums to show the motions of planetary systems. And you see here his drawings, how to use physical knowledge from Archimedes up to his time to have better designs of machines. Another contemporary of Galileo was Kepler. We already talked about Kepler. Kepler was one of those people who believed that when you make a mathematical discovery about nature, actually you understand natural laws and you act like a philosopher. You are eligible to talk about what the structure of the universe, about the firmament. He had a good amount of planetary data from himself and from his master Tycho Brahe. He used all of them, and then he discovered what planetary laws, we already talked about them, and he believed that mathematicians and astronomers can create a mathematical physics. By physics, we mean natural philosophy, that you can mathematize natural philosophy. Next week, we will see that. What was the name of the great book of Newton is The Mathematical Principles of Natural Philosophy, or Mathematical Principles of Physics. So he believed that it is, I'm just reading it, it was mathematics, especially geometry, which allows insight into the mind of God. We will see this idea, this type of thinking about universe up to even time of the beginning of 20th century. We will see that a new type of theology appears, which is called natural theology. How to understand or discover mind of God, because that was their main, what call business, their main interest, to find the creation, the rules of creation, the laws of creation. So if you discover about mathematics of this universe, you discover mind of God. And then in natural theology, you find out how to use knowledge that you have, scientific knowledge that you have, to connect it to, for example, a Bible, to miracles that people believed in it. For example, they believed in the flood. Okay, how can you scientifically talk about flood? In this new approach, since God was a mathematician, God was a physicist, then God used physical and mathematical tools to create flood. Not like this, okay? I create flood and flood comes here. No, they discovered about solar system, they discovered about gravity, and they used this knowledge as what? Tools that were in mind of God to have flood. Then we know that comets are moving around the Earth. That time they didn't know about the size of comets. They were thinking that comets were as big as the Earth. Then they theorized in this way that since this universe has a rule, we have universal laws, and God actually uses all these things, his own creations, to perform everything in this universe, then instead of just uh, thinking about a flood and creating a flood, he used all his creations, all his physical laws to create flood. And then when a comet approaches the Earth, because it has gravitational pull, Mr. Newton discovered that it is inverse square law, and it creates such and such amount of force, and it actually extracts water from oceans, and it creates flood, and then everything is okay. Everything is based on mathematics, is based on laws created by God. So even you see the impact of this approach, mathematical approach, had impact on theology. Instead of saying that God did this or that with angels, now you use mathematics and physics, that God, to create flood, he used gravitational laws and introduced, I don't know, a comet to do this. Last time we talked about this, and I pass it because Kepler, uh, he was thinking about the mystical aspects of universe, about Platonic ideas. Why do we have 5 Platonic solids? And he connected it to 5 planets, and little by little he developed this idea that each Platonic solid is responsible to hold one of these planets' orbits. But this study finally ended to a completely different result, and he introduced his 3 laws. Again, I'm not going to details, it's not astronomy class, but he showed that planets are moving around the sun on elliptical orbits, not orbs, not this onion layers, but on lines. And then when they approach the sun, they accelerate. When they are away from the sun, they slow down. And it took for what, I don't know, 50, 60 years to to Newton to come up and explain it in this way. I'm throwing it up. When it is away from this gravity, then it slows down. And when it falls down, because of increase in gravitational attraction, it speeds up. And the same thing happens here. The sun is the center of gravity of the solar system. Planets going away from that, okay, they slow down. And then when they approach, it is like falling towards the sun, and they speed up. And the third law was very interesting because he established a relationship between the period of a planetary motion and its distance from the mother planet. He said that there is a relationship between the period of, for example, Earth moving around the sun and its distance. The same relationship is valid, the period of Mars moving around the sun and its distance. So in mathematical expression, he said that p squared equals to a cube, or period squared equal to average distance cube. We will see this going to appear in Newton again. Okay, we already talked about this. Please pass and come back to again Bacon and his time, about his philosophy. Bacon was a very pragmatic, practical person. He wanted to realize physical world as it happens around us. So some people were thinking about atomism. That time people believed that atoms are particles, that they move in vacuum in a random way. So the question was this, and Bacon asked this, that how come that you have all these solid stuff, this universe, which is integrated, but it is composed of particles just flying in vacuum. We have to think about it different way. Even if we are thinking about atoms, then we have to come up with a new particle theory, how universe can work based on particles. So natural philosophy that time, or physics, was an attempt to find the best explanation for natural phenomena. We were in the period of moving from what a philosophical interpretation of everything into mathematical and experimental expression of natural phenomena around us. In the first half of 17th century, we find out another development, not only in philosophy, but also in physics and mathematics. And it came with René Descartes. Okay, this is his life. He studied in a Jesuit college. We already talked about Jesuits, and he joined army, and he was a very good mathematician. He learned about this corpuscular theory or particle theory. Then he went to Paris, and then at the end of his life, he went to Sweden to become the philosopher of the court there. And this is the just life of this guy. But what is so important about René Descartes is his philosophical role. To give an introduction to this, again, please pay attention. Let's start from Aristotle himself up to this time, up to the first decade of 17th century. Aristotle was the dominant figure in everything. And his philosophy worked like a glue, like a background, like a connecting cord to explain everything. From geocentric model, he provided the philosophical justification for that, to poetry. I always use this example because he wrote a very logical book about poetry, poetics. And there, when you open this book and read, you find out, okay, this guy 2,500 years ago had such a mind to analyze everything in this orderly way. So in poetry, he had his own effect, his own role. In, I don't know, sociology, the same thing, in physics and metaphysics. So everything was upon Aristotle's philosophy. Now, by the first 2 decades of 17th century, everything was shattered, collapsed. We didn't have that astronomy. We had a new astronomy. We had a new physics. We had a new understanding of motion of objects. We had new planetary rules, and there was no philosophy behind that. They were not upon a logic or philosophical thought to connect all of them and explain, again, this new universe upon a unified philosophy. Descartes played such a role, but he started from a different route. First of all, this is a period, the end of 16th century and beginning of 17th century. We see that a lot of skeptical philosophies emerge in Europe. What kind of skeptical philosophies? So people, in a short time, they found that solar system changed, their belief in motion changed, planetary motions changed, everything around them. And they actually puzzled with this question that really all these educated people, philosophers, religious authorities that we had, they were stupid in the past 3,000 years. How come they didn't realize all these things? So should we believe in all these things that are happening around us? If they didn't understand, how can I understand right now? How can I trust my reasoning? How can I trust Aristotle's reasoning and logic? So we had this skeptical philosophies in ancient Greek culture too. We had examples there from Zeno's paradoxes to, I don't know, Sextus Empiricus. They doubt about the way that we understand uh, everything around us. So we are like a computer. We have input and we have a processing unit. What are our inputs? 5 senses that we have. So we get information about all this universe with 5 senses, and then we send it to our processing system, or UPS, and then, I'm sorry, central CPU, central processing unit, and we make our science. So these people asked, how can we trust these 5 senses? Always, they're not accurate, or they can make mistake. And how about our reasoning? We can make mistake in our reasoning. We can have a lot of, I don't know, illusions and a lot of misunderstanding. Then really people ask this question, how can you prove that we exist right now? We are not like dreams. In modern terminology, we are not in, I don't know, like a computer programming in a multiverse, I don't know, digital world. And you can connect this question to Descartes' very famous motto, I think, therefore I am. Cogito ergo sum in Latin, it means that the moment that you start to think about these things, it means that you exist. You are not a dream. You are not virtual. You are real. And since we have this starting point that we exist because we think, then the next step is how to think. Okay, that's why he started to talk about methodology of thinking. Okay, his first book about the first philosophy, there he starts to establish basis for everything, and it starts with this skepticism that you have to verify everything. You have to verify, measure it with logic, with mathematics, with all principles that you have. Move from authorities, from Aristotle, from religious authorities, from other philosophers, and first doubt about everything, verify everything, and then little by little build your philosophy. So Descartes believed in a kind of mechanical world. He believed in a kind of clockwork. He believed that God created the universe based on certain rules. He gave the first motion to the entire universe, and he's away. And the entire universe is moving based on those rules. He believed that everything is made up of matter in motion, particle in motion. Particle has a space, it occupies a space, and it moves in space. And in this way, or thinking material, res cogitans, or thinking material, can understand or analyze these things, and then can have impact on the material world. He believed that only human being has this thinking stuff. Animals are just machines. You can say programmable machines. They are doing just simple things. He believed that animals don't have feeling. They don't have power of abstraction. They cannot write poetry. They cannot understand mathematics, and so on and so forth. This is only human being having this capability. And uh, I'm connecting it to technology, and he believed that you can make all these animals. Though we don't have enough technology, but you can make androids, you can make robots, because they are just machines. For example, this Descartes duck is very important. Duck is what? Fly is physics. Sound is physics. Digestion is chemistry. Vision is physics. And the rest, duck is not thinking. The duck is not able to, I don't know, solve a mathematical problem. That was Descartes' idea. Then we can make it. Anyhow, back to Descartes' idea. So we have an interaction with the physical world through these particles, and then these particles impact, or for example, nerve system or eyes. We analyze them, and then we can act on what material world. Descartes' world was uh, colorless, smellless, odorless place. Why? Because based on Aristotle, when I have, for example, this blue marker, Aristotle says there is something blue, a blue quality here. Or you smell a rose, there is a quality and odor there. In Descartes' universe, I see it blue because the size and motion and orientation and the speed of the particles connecting this object to my eyes in a way that it creates a sense of blueness here. Okay, and the same thing about the odors that we feel. Descartes says that the universe was created by God. There was primordial matter there. Because of this motion, they collided, they rubbed to each other, and then it created three types of matter here, and they are responsible for whatever we see in this universe. Descartes believed in multiplicity of universes or worlds. As you see, this is his universe made up of vortices. Each vortex is a solar system, and look at the shape of the solar systems there. They are elliptical. And it was a clockwork, as I said. God created the universe. Now the universe is working based on its own rules. And since, bottom line is here, since it is particle in motion, then you can express everything in this universe mathematically. When you think about Descartes, what comes to you from mathematical part? You are familiar with what Cartesian coordinates. You have a three-dimensional coordinates, and you have particles. Each particle comes with three associated numbers on x, y, z, and when it moves, so these x, y, z's are changing, and you can easily explain motions and happenings in this universe in a mathematical way. He introduced, for example, different types of these particles. So you see here, he tries to explain magnetic forces. Some of these particles are like screw, and then they enter into body, they bring them closer, and or when they are rotating in different direction, they create repulsion. How do we feel fire? So particles agitating our nerve system in a such and such speed, and then nerve system brings it to our CPU, and then CPU tells your body to move back, or we see in such and such way. Again, everything is related to particle in motion. And from a slingshot to rainbow in Descartes' philosophy was explained based on matter in motion. Descartes was a prophet before Newton to explain everything. But when Newton came to the scene, everything was changed because Newton was able to explain everything, not with this philosophical approach, but with a completely mathematical approach. Okay, let's stop here. This is my last slide. This is the Cartesian coordinates that you see. I already talked about this. And we talked about the importance of mathematics, geometry in understanding of natural phenomena. Okay, folks, let's stop here. I wish you a very good weekend. And if you had any question, please, about your essay and your performance, please attend office hours. One of the students asked me to talk about a different subject, but I have another class after this. And unfortunately, I cannot spend long time. So either send me an email or we can talk on Monday during my office hours, okay? So you have fun during this weekend and see you guys on next Monday. Bye, everybody.